Welcome to UXL, where you can learn new skills anytime and anywhere. Visit uxl.com to explore our full course selection. This lesson is part of a larger course. Check the video description below for a link to the full course where you can enroll. If you enjoy our content, please like and subscribe. For your convenience, the course cover displayed on your screen provides the complete course title and lesson title. Let's proceed with the lesson. Lesson: Techniques for validating model performance. Techniques for validating model performance are crucial in the development and deployment of machine learning models, particularly within the broader scope of the GenAI life cycle. As models are increasingly relied upon for critical decision-making processes, ensuring their accuracy, reliability, and generalizability is paramount. This lesson delves into the most effective techniques for validating model performance, highlighting their significance, methodologies, and practical applications. Model validation is a fundamental phase in the machine learning lifecycle that ensures a model's ability to generalize to unseen data. The primary objective is to assess how well a model trained on a specific dataset will perform on new, unobserved data. This process mitigates the risk of overfitting, where a model learns the training data too well, including its noise and outliers, and subsequently performs poorly on new data. The validation process involves several key techniques, each with its strengths and limitations, and understanding these is vital for selecting the appropriate method for a given scenario. Cross-validation is one of the most widely used techniques for model validation. It involves partitioning the dataset into multiple subsets or folds and training the model iteratively using these subsets. The most common form is k-fold cross-validation, where the dataset is divided into k equally sized folds. The model is trained k times, each time using k1 folds for training and the remaining fold for validation. This process ensures that every data point is used for both training and validation, providing a comprehensive evaluation of the model's performance. Cross-validation is particularly useful in scenarios where data is limited, as it maximizes the use of available data without requiring a separate validation set. Leave-one-out cross-validation is a special case of k-fold cross-validation, where k is equal to the number of data points in the dataset. Each iteration involves using all but one data point for training and the single remaining data point for validation. While OCV provides an unbiased estimate of the model's performance, it is computationally expensive, especially for large datasets, as it requires training the model as many times as there are data points. Another critical technique for model validation is the holdout method, which involves splitting the dataset into two distinct sets, a training set and a test set. The model is trained on the training set and then evaluated on the test set. This method is straightforward and computationally efficient, making it suitable for large datasets. However, its main drawback is that the model's performance estimate can vary depending on how the data is split, which can introduce bias if the split is not representative of the overall data distribution. In addition to these techniques, bootstrapping is another method used for model validation. Bootstrapping involves repeatedly resampling the dataset with replacement to create multiple training sets. The model is trained on each of these sets and evaluated on the data points not included in the current training set. This method provides an estimate of the model's performance and variance, offering insights into its stability and robustness. Bootstrapping is particularly useful in scenarios with small datasets, as it allows for the creation of numerous training sets from limited data. The choice of validation technique can significantly impact the perceived performance of a model. Factors such as dataset size, computational resources, and the specific application context should all influence this decision. For instance, k-fold cross-validation is often preferred in academic research and when computational resources are sufficient, as it provides a robust estimate of model performance. In contrast, the holdout method might be more appropriate in industry settings where computational efficiency and speed are prioritized. Model validation also involves the use of performance metrics to quantify how well a model is performing. Common metrics include accuracy, precision, recall, an F1 score for classification tasks, and mean squared error or root mean squared error for regression tasks. Each metric provides different insights into the model's performance, and the choice of metrics should align with the specific goals of the application. For example, in a medical diagnosis scenario, recall might be prioritized over precision to minimize false negatives, ensuring that as many positive cases as possible are identified. Furthermore, it is essential to consider the context and domain in which the model will be deployed. For example, a model used in financial forecasting may require different validation techniques and performance metrics compared to a model used in image recognition. Domain-specific challenges and requirements should guide the validation process to ensure that the model meets the necessary standards for accuracy and reliability. Incorporating validation techniques into the model development process also involves understanding the potential biases and limitations inherent in the dataset. Bias can arise from various sources, including data collection methods, sampling strategies, and historical trends. Techniques such as stratified sampling, where the dataset is divided into subsets that reflect the distribution of key variables, can help mitigate these biases and ensure a more representative validation process. Ultimately, the goal of model validation is to provide a comprehensive assessment of a model's performance and to identify areas for improvement. This iterative process of evaluation and refinement is critical for developing robust, reliable models that can effectively generalize to new data. By employing a combination of validation techniques and performance metrics, and by considering the specific context and domain of the model, practitioners can ensure that their models meet the necessary standards for deployment. The techniques for validating model performance are an integral part of the GenAI life cycle, ensuring that models are not only accurate but also reliable and generalizable. From cross-validation and bootstrapping to performance metrics and bias mitigation, each technique offers unique insights and advantages. By understanding and effectively applying these techniques, practitioners can enhance the quality and robustness of their models, ultimately leading to more effective and trustworthy AI solutions. This concludes the lesson. We trust you found this video informative and engaging. To enroll in the complete course, please use the link provided in the description below. At UXL, we are committed to your learning journey. Each course offers a certificate of completion, online support, and downloadable resource files to enhance your experience. If you found our content valuable, we invite you to like this video and subscribe to our channel. Thank you for joining us, and we look forward to supporting your continued pursuit of knowledge.